Good morning, good afternoon, good evening, wherever you are, and thank you for joining us for this AMETEK Solidstate Controls webinar on understanding DC system designs. Thank you for joining us today. We understand that you are very busy and you have many things to do in your day-to-day lives, whether it's your engineering position or working in the power plants or petrochemical industry. So we do appreciate you joining us. If you could please type in the chat bar and let me know that you can hear me, that would be very, very good. That's always a good start. And we'll just give it a few more moments for everybody to join us, and then we can get started. So while we are waiting for everybody else to join in, just go over the introductions. My name is Craig Williams. I am the Senior Technical Manager for AMETEK Solidstate Controls, and I am located in the Stafford office, which is just outside of Houston, Texas. Can't you tell from my accent? I have 20 years in the industrial UPS industry. Oh, thank you everybody for telling me you can hear me. Very, very good. Yeah, I have 20 years in the industrial UPS industry, and I've worked on many different UPSs, different manufacturers, so I have a wealth of experience when it comes to that. Regarding the presentation, there will be a lag of around 30 seconds between you hearing my voice and for me seeing any questions or comments that you put in the chat bar. That is because Webinar Jam has to send this webinar out onto iOS devices, Windows devices, and it has to transcript all of that information and send it out into the world. So although it is live, there is about a 15 to 30 second delay on when you hear my voice to when you type something in the chat bar. And I do try and leave the answers, the questions until the end of the webinar. But if there is something pertinent to what I am discussing, I'll try and pick it out as I go, if possible. The platform we use is Webinar Jam, and it has a panic button. So if something goes wrong with the webinar, if we lose connectivity, a whole host of things, I suppose, can happen. I have a button that I can press, and that creates a brand new webinar, sends everybody an invite, and we can carry on from where we left off. The webinar will be recorded. Webinar Jam records the webinar for us. Unfortunately, the way that it does it for replay is you can't fast forward, rewind it, and go to different points. So what our fantastic marketing department do is they download that video and then they upload it to our YouTube channel, which you will get a link to in the chat bar later on today. The webinar will last round about 1 hour, depending on how much I yap, and sometimes I can get a little long-winded, but we do try and keep the webinars to around about an hour, and obviously it depends on how many questions get answered at the end as well. So without further ado, we will move on and go over the learning outcomes. So today, hopefully, you're going to be able to understand the most common DC systems, understand what a DC system is designed for, discuss the advantages and disadvantages of the different designs that you can implement, discuss power flow and general operation of each design, and discuss common misconceptions that are out there. Okay. So here is the most basic single line drawing for a DC system. And obviously what you can see is we have an AC input on the left-hand side here. Now, with AMETEK SCI, we only make three-phase input charger systems, but there are other manufacturers who have single-phase inputs if necessary. But for us, it's usually going to be three-phase 480 or three-phase 208 that goes into the charger. You're usually going to have an AC input breaker, so you can disconnect the power to the charger. Then you will usually, in an industrial charger system, you're going to have an isolation transformer. And then you're going to have your rectifier bridge. you're going to have your bridge that turns your AC into DC. And then that comes out on this bus here. That's going to be your DC bus. And that DC bus splits off in two directions. Obviously, one, we're going to go down through a breaker to our battery down here. And then the other branch is going to take you to your load, your DC panel somewhere where you can send that out to your DC loads. So that is the most basic of single line drawings for a DC system. Now, in plant operation, this is actually a better way to do it. You can see that you have your MCC here. Your MCC obviously has a bucket, and that is going to have a breaker on it. And then that goes into, you can see this dotted line here. This is actually your charger. But the difference that you can see on this drawing compared to the last drawing is the way that we connect the battery and the loads at the DC panel. You can see here that the battery is now connected at the DC panel. You can either have a breaker here onto the main bus, or in some really critical operations, I think there's a drawing for that later on, where you'll see where the battery is connected without a breaker, if you don't want there to be a single point of failure between the battery and the loads themselves. And then you can see inside the DC panel, we have all these breakers. And what you'll also see here is we have a breaker that you can isolate the charger from the DC panel using that breaker there. So this gives you a little bit more flexibility than the previous drawing. Now, in this system here, what the plant has done, and I've actually seen this in person on a few examples, is this is not a good design. What they actually did is this tie point here is actually the output terminals of the charger. And the output terminals of the chargers are usually a bolted connection onto a bus bar. In AMETEK SCI chargers they are. And what they do is they put two sets of cables on that tie point, which is a convenient point to connect both your battery and your load cables. But what you'll see when we go further into this presentation is it causes issues if you want to do maintenance on any part of the system. It makes it very, very difficult for you to disconnect either the charger and the battery or the battery and still have your load circuits powered. And if I go on here, you can see exactly what I mean. So this here, this is your positive and your negative output from the charger. Okay, and what they've done is this back cable here, this is the battery cable, and this front cable here is the load cable. So you can see, say we had a problem in this charger and we wanted to keep the load circuits powered up with the battery, with the battery, this one at the back here. That's going to be impossible for us because we would have to undo this bolt here to disconnect the charger. And in doing that, in loosening that bolt, we are going to make a disconnection to your load circuits, and your load circuits are going to be dropped. So this is not although it's a convenient way to connect your load and your battery to the output of the charger, it is definitely not the best way to do it, and it's not the recommended way to do it either. Okay, so hopefully that gives you a good example of where not to connect your load and your battery cables. And the next mistake that I've seen in many of the plants that I've been to is where they connect the load and the battery at the battery terminals. And in this next picture here, you will be able to see that. What you can see is on many lead acid systems, you will see a big bus plate, this big bus plate here that is connected to the main positive using these bolts here. Okay, and then what the plant does is they'll connect the cable from their charger to the battery at this point here, and then they'll connect their load cable to this point here and take that out to the load. And obviously, once again, if you want to replace the battery, it's going to be very, very difficult for you to do that and keep your load panel powered, even if you had a temporary battery connected to it, because how are you going to connect this cable here while the system is live? It's just not a good situation if you wanted to replace this battery here, to have both cables connected like this. We have a question there. How can you correct the mistake if you already have it? That's actually a very good question. What you have to do is you have to get with your plant engineers and figure out how you can get to this system here. Basically, you have to look at your DC panel and see if there is room for an additional breaker. Make sure it is rated correctly for the output rating of this charger, and then also see if you have enough room for this breaker here. Now, you'll definitely have to make sure this is rated correctly, because that will carry the full current of the battery to all of the load circuits. So it will require some engineering, and it will probably require a load outage, although there are ways and means around it, but it usually means you have to tie in either a temporary charger or a temporary battery into your system while the system is hot. So it can be done, but it does introduce some safety issues, which could cause some problems, but it can be done. And here's another example of a battery. What some people do is, you can see here, this bottom cable here is from the charger, and then what they'll do is they will connect their load cables on the back side of this post here. And once again, if you ever had to do maintenance or a capacity test on this battery here, then you're not going to be able to loosen this bolt and separate these wires. That will cause an issue to your load circuits. So it's not a good design. So in truth, this drawing here is one of the absolute best designs you can have. This is a dual redundant charger system, and you can see that charger 1, rectifier 1, is fed from MCC1 from its own bucket, and rectifier 2 is fed from a separate MCC. So it's giving you possibilities now, because obviously if somebody is going to do maintenance on MCC1, then MCC2 is going to remain powered and can continue to power your DC circuits through rectifier 2. So this gives us some redundancy. Once again, we have our AC input breakers on each charger, and then we go into the charger, and then each charger has a disconnect in the DC panel here. Okay, and on this system here, we only have a single battery. The next slide is going to show you what it's like if you have 2 batteries, but it gives us complete flexibility in what we want to do. Let's say, for example, rectifier 1 fails in this situation. What we can do is we can open this breaker here on the DC panel, and therefore that makes this point here volt free. Once we isolate the MCC, lock and tag out that, lock and tag out that, lock and tag out that, then we can actually take this whole rectifier out and replace it with a new one if necessary, and the power flow goes through here through rectifier 2 and keeps the batteries charged and your load circuits powered. So this gives us a huge amount of flexibility. The only issue that we have on this system here is we only have 1 battery. So if we do have a fault on this battery here and we need to replace it, then what we would have to do is open this breaker here, and that means we wouldn't have any battery backup when we were performing either the maintenance or the replacement. So this is nearly the best way to design your DC systems, but not quite there. And as I mentioned earlier, in some highly critical systems, they will not have a breaker between the battery and the DC bus here, because especially for DC lube oil pumps, you don't want anything to separate the power between that battery and the DC lube oil pumps on a turbine. So you want the most reliable form of power whatsoever, and sometimes they will remove the breaker from that arrangement. Okay, we've had a couple of questions on diodes. I am going to get to that in just a moment, hopefully. But this one here gets the gold star. Okay, we have exactly the same dual redundancy on the rectifiers, the chargers, but now we have battery 1 and we have battery 2, each protected by their own DC disconnect. And that means if battery 1 fails, we can go in and we can open its DC input, DC breaker, and we can leave battery 2 supplying the load circuits if necessary, or being charged from both chargers. And we can go in, we can replace this battery, we can do maintenance on it without jeopardizing the load circuits whatsoever. Now, obviously, it's more expensive because you have 2 chargers and 2 batteries, but down the line, it's going to save you much more in maintenance costs and the ability to have flexibility when you have issues with either a battery or a charger. And in most industrial systems, you're expecting 20 years, 10 to 20 years out of your battery and your charger. So this gives you the best flexibility for your DC system. Okay. So gold star for this one. So what I'm going to do is I'm going to go through the power flow for a DC system and show you how the power is flowing through the load circuits, the battery, in each example. So in normal operation, your MCC is going to feed into your rectifier through its AC input breaker, and it's going to change the AC into DC within the rectifier charger. And actually, at this point here, I want to clarify that rectifier and charger are interchangeable terms in most circumstances. They mean the same thing. To rectify an AC signal is to change it from AC to DC, and a charger does exactly the same. The only thing with the term charger is it usually means that there is going to be a battery connected to the system because you're going to charge the batteries. There are some circumstances where you will have a rectifier that does not have a battery connected, and therefore rectifier would be a better term, but they are interchangeable. Okay, so the power flows through AC to DC, and then it goes to the DC bus into the DC panel, and then it's actually the charger that is feeding the load power to the circuits. The battery is just receiving a trickle charge. If you put an amp clamp around this point here, and depending on your battery size, there's going to be a very, very small current. It's going to be between 0 to 1 amps DC going to your battery when it is in trickle charge mode, when it is fully charged. Okay, all of the current from the charger is basically going to be going through here to your load circuits here. Okay, so that's in normal operation how that would work. Now, if you had a failure, either grid power has been lost or something has happened at the MCC and we have lost AC power to the system, the battery now takes over, and the battery will supply load to your DC circuits. Okay, there's no switching involved. It's just like pulling the plug out from your laptop, the AC input to your laptop. There's no switching. The laptop carries on going regardless because the battery is in parallel with the DC bus. But do bear in mind, obviously, if you've lost power at the MCC, this breaker here is going to be closed, and this breaker here is going to be closed. So don't think that you will have no power in your rectifier on its output terminals. There will be a backfeed from the battery into the charger. There'll be no power draw, but there will be backfeed on the positive and negative terminals in the charger in that situation. Okay. And then when power comes back on again at the MCC, then what happens is the charger goes back to powering the load circuits. And then now it is actually supplying power to the battery. And depending on how discharged the battery is and the size of the battery will depend on how much current is flowing to the battery at this point here. If it's a very large station battery, it could be hundreds of amps that's going into the battery to get it recharged, depending on the design of the system. Okay. Now, in the best case scenario, when you have a dual redundant charger and two batteries, the power flow is both chargers are connected in parallel. The AC will be converted into DC, and then the DC gets combined on the DC bus within the DC panel. So they are in parallel. So both chargers will be supplying power out to your load circuits. And this brings up a contentious issue. Okay, they're saying that most people say that the chargers should share the load. Now, I go into this later on. So basically, if you have 20 amps of load on your DC panel, most people would say you should have 10 amps on charger 1 and 10 amps on charger 2. And in an ideal, perfect world, that would be the case. But unfortunately, we don't live in an ideal, perfect world. And you will find that the cable between charger 2 and the DC panel is slightly longer than the cable between rectifier 1, charger 1 and the DC panel. So therefore, the cable resistance is different. So therefore, one charger will have a slightly higher voltage than the other at the DC panel and will take more load. And like I said, we go into this in a little bit more depth in the misconception point of this presentation. But at this point here, if your chargers aren't sharing load, it is not generally an issue. And there's ways to check if both chargers are working correctly, and we'll get to that later on. Okay. And in this system here, both batteries will receive a trickle charge when both chargers are connected. So let's say we have a failure in MCC2. Therefore, we have no AC power going to rectifier 2. Okay. Well, what will happen is rectifier or charger 1 will continue without any switching or whatsoever. It will just say, okay, I need to supply all the power now. So remember we said earlier, this would be 10 amps and this would be 10 amps. If we had 20 amps on the load panel, all that would happen now is instead of it being 10 amps there, it is now going to be 20 amps coming out of charger 1. Okay. And it continues, it continues to feed both batteries with its trickle charge. So both batteries are still being kept at their full charge voltage. But once again, do bear in mind that there will be feedback into the output terminals of rectifier 2 or charger 2 at this point, because this disconnect here is closed and this disconnect here is closed. All we've done is lost power. Okay. Now, if we had a whole plant outage, if we'd lost complete power to the plant, so MC1 is out, MC2 is out, then basically both batteries in parallel will feed power to the load circuits. Okay. Obviously, there will be voltage going back to the terminals inside the charge 1 and charge 2, so be careful about that. But when both systems lose AC power, that's when the batteries take over feeding the load. So here's the advantage of parallel systems. I mentioned it earlier, but what you can do is you can replace a whole charger without affecting your load circuits. As you can see here, we have lottoed MCC2, okay? We have lottoed this breaker here. So we have no power at these terminals. We have no power at these terminals. Those wires can be disconnected, and we can take rectifier 2, we can completely physically remove it, and then we can install a brand new charger, power it up, test it. What we can do is, once the charger 2 has been replaced, we can connect the cables, we can re-energize Lotto, we can remove the Lotto from MCC2, and we can energize the charger, keeping this breaker here open, and we can do all the testing on this system. And then once everything is okay, the cables are connected. The last thing we would do, knowing that the charger is okay, we would then close this breaker here. So you can see, so the load circuits won't be affected. You don't need to do this in a turnaround. You don't need to wait for a plant outage. When you have a parallel redundant system, you can easily replace a charger without affecting the load circuits whatsoever. And the same can be said for a battery. You can see here that battery 2 has failed. We want to replace it. So charger 1 stays on, charger 2 stays on. All we do is lock out, tag out the battery disconnect going to battery 2, and we can replace that battery, or we can do a capacity test on it. We can do whatever we want to replace that. Somebody just asked, they've never heard of Lotto before. It's lockout, tag out. In other words, it's a way of confirming isolation of a breaker. It's putting a lock on it and a tag to say who put that isolation point on, and that can only be removed by the person who put the isolation on in the first place. It is for electrical safety. Okay. So what are the typical uses for DC UPS systems? So the typical uses are switchgear, tripping, and closing supplies. Obviously, that's your main MCCs. All of those MCCs have springs and coils that open and close the breakers automatically. So you need battery power to charge and discharge those springs if you lose AC power. DC lube pumps on turbines. What you need is that turbine shaft has to be protected at all time. The oil into the bearings on that turbine has to flow at all times. So even when there is a grid failure, that pump has to pump the oil through the bearings as the turbine spins down. So that's DC systems keep the batteries charged to allow the batteries to drive the DC lube pump on turbines. Very critical. If the bearings stop having oil pumped through them, they will overheat, and the shaft on that turbine will bend, warp, and that is extremely expensive. You also find that, especially on offshore platforms, you will have DC-powered DCS systems. Now, in most petrochemical plants and onshore facilities, they usually use an AC UPS that then powers the DC, the AC to DC converter in the DCS system. But offshore, there are DCS systems that are designed for 24 volts or 48 volts DC. They're quite common. Telecommunication systems, I'm not hugely familiar, but a lot of the telecommunication systems for your phones, your mobile phones, they need 48 volt DC systems to keep them powered up. And some instrumentation requires DC power. Analyzers and things like that, they can run off DC power as well. It's all down to the engineer's choice. So that is the main uses for DC UPS systems in the industries that we work in. So now we're going to discuss the common misconceptions. We're going to go through this, and I've got the reminder of the diode question, so I'm not going to forget that later on. So the first misconception is my battery is 135 volts, therefore the battery is good. Well, a very, very common misconception, actually. But here's a circuit that hopefully is going to help you understand why that is not the case. So this is your 120 volt input to your house. Okay, so let's say you have 3 lamps plugged into 3 different sockets within your house. Okay, so this is lamp 1, this is lamp 2, and this is lamp 3. If you measured the line to neutral voltage across each lamp, you're going to measure 120 volts. Hopefully you all understand that that's a parallel circuit, and all 3 lamps will see 120 volts. Okay? Now, if you unplugged this lamp that was there, if you unplugged that, but you went to the socket that it was originally plugged into and measured across the hot and the neutral, you're still going to measure 120 volts AC. Okay, the lamp has disappeared, but there is still power going to that socket. Okay? And that's exactly the same with a DC battery system. So in most industrial plants, your DC system is going to be a 60 cell, it's going to be a 60 cell VRLA, valve regulated lead acid battery, or a vented VLA, a vented lead acid battery. But you're going to have 60 cells, and that gets charged at around about 135 volts DC. So if you measured the positive of this battery to the negative of this battery, 135 volts. And if you measure the positive on this battery with the negative of this battery here, 135 volts. Okay, hopefully that makes sense. But guess what? If you removed that third battery, if you lifted the positive cable and you lifted the negative cable, but you still had the ability to measure it with a fluke voltmeter, you're still going to measure 135 volts DC at these points here. Okay, hopefully that makes sense. So therefore, I'm going to skip this one here. So therefore, if you have one battery and you remove it, you're still going to have under 135 volts here. And the reason that I'm trying to drive this in is because this next picture here is if you have an open circuit cell in this battery, okay, that means the battery is useless. Absolutely useless. The battery cannot supply power when there is an open circuit cell. It is like somebody just splitting the wire here. If you split that wire here, no power is going to get to the battery. But if you do it within the battery itself, no current can flow through an open circuit cell. But if you measure the positive and the negative of the battery terminals, you're still going to get 135 volts because that is what the charger is putting out. Okay, so even though this battery is now completely and utterly useless, you're still going to measure 135 volts at the terminals. So when people say, oh, I measured my battery, it's got 135 volts DC, so it must be good, that is not correct. You could have an open circuit in your battery. You're still going to measure 135 volts. That voltage doesn't tell you anything about the health of that battery whatsoever. So never, ever use the voltage of the battery with the charger connected as giving you the state of health of the battery. That is completely and utterly incorrect. All you are measuring is the charger voltage at this point here. Hopefully that explained that misconception. Let me do this. So this one here says, I can disconnect my battery online. Another common misconception. So in most cases, AC goes into your battery. Oh, let's change color. Let me just do this. One moment. It's not allowing me to change the color. So you have your AC coming in here and your DC coming out here, and your batteries are being trickle charged at this point here. Okay, so what we're saying is you can remove this battery and your load circuits are going to be remain powered and okay. Now that is not the case. Now, there are some circumstances where it may be okay, but there's a lot more that goes into it. Now, many charger manufacturers, especially older chargers, they didn't have the DC filtering that modern day capacitors have. In fact, some chargers didn't have any capacitors inside them for filtering purposes. Okay? So if you look at this picture here, if you have an unfiltered charger, you have AC coming in on this side here, 135 volts, and that is a sinusoidal waveform. And the way that the charger creates DC is it takes this portion of the AC and flips it up above the 0 volt line, which is basically DC. And you can see that in this example here. This is a 0 volt line. This is probably around about 140 volts, the max. And we're going from 0 to the max, and then it's called pulsating DC. Okay, it's still DC because it's all above the 0 volt line, but it's not what you would expect out of a modern day DC system. You would expect a nice flat DC. So therefore, when you have a battery connected to this system, the battery acts as a capacitor. And what it does is it fills in these gaps, because remember, in a battery, you have plates. Okay, and any plate that is in parallel with each other acts as a capacitor. So the battery has capacitance and acts as a filter itself. So if you remove that battery, okay, what your load circuits are going to see now, instead of a flat DC, they're going to see this high ripple waveform. Okay, it's going from 0 volts up to the peak and then back down again. And some circuits, especially relays, don't like that. Some relays will start to chatter. It's not a good situation. So if you disconnected a battery on an unfiltered charger, you can immediately cause issues on your load circuits. So that is one example of why you can't just go in, open a battery, disconnect, and expect everything to continue to work. That is not the case. The other reason why you can't do that is because of the design of a DC system. The charger is very, very rarely designed to carry the full load current of a system. Okay, the charger is usually sized for its recharge time. So basically, I'm saying here that a 30 amp charger could charge a 100 amp hour battery in about 8 hours. So the design engineer says, okay, I have a 100 ampere hour battery. So this battery here is 100 ampere hours. So I can connect a 30 amp charger to my 100 ampere hour battery, and I know my battery is going to be charged back up after a full discharge in 8 hours. But that doesn't mean that you can't connect maybe 100 amps of load to your system. And it depends on what kind of load you have. In most circumstances, once again, in a switchgear charger, you're going to have tripping closed coils, and they're not constantly on. So a load profile has to be designed by the engineer. But it is, in many cases, your load circuits are going to see far more current than the charger itself can actually supply, because that's not what the design of the charger is for. So in that system, If you remove the battery by locking out this breaker here, yes, in normal operation, your load circuits are going to remain powered and you're not going to have a plant outage situation. But if you then have a fault on one of these branch circuits and the tripping and coil springs are called into action, the common charge motor inrush can be somewhere between 20 to 30 amps DC. Okay, so that sudden inrush, and it actually can be more. So that sudden inrush may cause an overload on the output of this charger. And the only way a charger can prevent an overload is by reducing its output voltage. So if one or more tripping and coil springs come on at one time, that is going to severely overload the charger. It's going to cause this voltage bus to drop, and it may cause the other load circuits connected at the DC panel to drop out as well. So you cannot, in theory, you cannot disconnect a battery from a system and think that everything is going to be okay. Yes, in some circumstances, your power will continue to your load circuits, but if something is called into action without a battery, you may have issues. And that is why I take such a, I have a problem with people who sell battery eliminator chargers. There is no such thing as a battery eliminator charger. You cannot eliminate a battery. There is no charger out there that gives you any more of a backup time than about 1 second, because it's all basically down to the capacitors inside the charger. You're going to get 1 second if you have a power failure. So don't get lulled into this false sense of security. When somebody sells you a battery eliminator charger, it does not eliminate the battery. You still must have the battery connected. All they're doing in a battery eliminator charger is adding more capacitors. So if you absolutely had to quickly replace a battery, you could open the breaker, replace the battery immediately, and your load circuits would still be powered. If something happened, if on the DC bus, if things were called into action while you were replacing that battery, all bets are off. Okay, we don't know what's going to happen when you have no battery connected. So the best thing to do in that circumstance, let me see if I have, let me go back here. The best thing to do is, if you ever have a battery failure, hopefully your engineer has designed in an additional breaker. And what you can come in and do is you can come in and get a temporary battery and connect it onto that breaker there. And then that will allow you to open this breaker, replace this battery here, and you now have a temporary battery here that is going to maintain power if you have a power loss or if your tripping and coil springs are called into action. But do make sure that this temporary battery is exactly the same ampere hour capacity as the battery that you are replacing. Okay. Let me just take a drink, and I'll stop talking for a moment so I don't make your brains explode. So hopefully things are interesting so far. So now we're going to move on, and another very common complaint I hear is the ground fault is on my battery charger. Okay. Now that is, I can understand why people think that the ground fault is always on the battery charger, because the alarm for the ground fault, there's usually a lamp on your charger here that says ground fault. So everybody thinks that if there is, if the light comes on the charger and says ground fault, well, then the fault is on the charger. That's not the case, because all of our DC circuits are connected on this DC bus. So the battery is connected on the DC bus, and all of these load circuits are connected on the DC bus, all in parallel. Okay, so any fault on any of the load circuits or on the battery itself will cause a ground fault to show up on the charger terminals too, because they're all in parallel. So what most charger manufacturers do is they have an isolation transformer at this point here. And what that isolation transformer does is it gives complete galvanic isolation between our AC input and our DC bus, which means the ground that has been created in here, the neutral is connected to ground in the MCC. But once we get to the secondary of this transformer here, there is absolutely no reference to ground on this circuit here, unless it's been intentionally done. And if, just follow me as we go through these slides and you'll understand more. Okay. So, and what I mean by this is, let's take 120 volt AC input into a transformer to explain what's going on. So the neutral for any system will be grounded at the source, and it should only be grounded at one point. Okay. So the neutral is intentionally tied to ground on the primary of this transformer. But you can see here that this is an isolation transformer. There is absolutely no connection between the primary and the secondary. No electrical connection whatsoever. Okay? So, although we do have 120 volts AC line to neutral on the secondary of this transformer, it is now a separately derived source. And there is no connection to ground unless somebody has actually done that. So, in theory, I am not recommending anybody do this, but in theory, what you could actually do in this circumstance here is a man could come along and actually, with his bare hand, he could grab onto the live of this secondary of this transformer here, and absolutely nothing will happen to him. All that will happen is through his body, he now creates he will tie the hot to ground. No current will flow. He will not get an electric shock, but he will just tie this point to ground. It is just like, and what I'm trying to say is, somebody, if they wanted to, if they really, really wanted to, you could actually get a wire and you could tie this to ground. Not a problem. And that is on the hot side. If that's what you wanted to do, you could do that. But in most cases, what you would do is you would tie, on an AC system, you would tie the neutral back to ground again and give it a separately derived neutral to ground connection. Okay? And follow me, there's a reason why I'm going through this. Okay, so just stay with me. So, if you measure at this point here, hot to ground with a fluke, you're going to get 120 volts AC. But on this secondary side here, if you measure from this point here to ground, this point here, there is no reference anymore. What is the voltage going to be? Well, who knows? There is no reference. So there should be no voltage, actually. There should be no potential difference. There can be stray capacitance, just the way that cables are run and other things that give a ghost potential. But if you put any form of load on that, it would disappear quickly. It is just a ghost resistance. I mean, a ghost voltage. It's not actually a true voltage in this system here. So you would not measure any voltage between hot and ground and neutral and ground on this system, because it has not been given a reference to ground. It doesn't know where ground is. Okay? So, once again, we have that exact same circuit here. There is no connection to ground on the secondary of this transformer. And now all we've done is we've put a charger here. Okay? So now we have our positive here, and we have our negative here, and we have our battery at this point here. If you measure from positive to ground, What is the voltage going to be? Who knows? There is no reference, so there should be no voltage. Once again, there can be stray capacitance and other things that give a ghost potential. And actually, somebody has just put in a comment there. Most people, if this is a 135-volt battery, they would expect to see about 67 volts from positive to ground and 67 volts from negative to ground. Okay? There is a reason why you expect that. And I'm going to go, hopefully, I think it's this next slide. Okay? No, I just go on and say, okay, if you go from negative to ground, you should really see 0 volts. But here's the reason why. Because inside the charger, we have created a ground fault detection circuit. And this slide here shows you the most basic ground fault detection circuit there is. And that is 2 lamps in series. So let's say, once again, this DC bus is 135 volts. Okay? And we have 2 lamps. And we're saying that they're both 120-volt lamps, 5 watts, which means if you do the ohms law calculation, they're around about 3K ohms. Okay? Whenever you put 2 resistances in series across a voltage, what that does is it creates a potential divider. And all we've done here is we've connected the ground to the center point of both of those lamps. Okay? So 2 resistors in series on the same value create a potential divider that has a ratio of 50-50. So what that does is, these lamps, even if you didn't have this connection to ground here, now you would measure half the voltage on one side and half the voltage on the other. Okay? If you measured from this point here to this point here, we're not talking about, remember, this ground has disappeared. You would measure 67.5 volts, and if you measured from this point here to this point here, you would measure 67.5 volts. That's what 2 resistors in series does. So that is where your half voltage comes from, is because your charger has a ground detection circuit in it. So how does this system detect a ground? This very simple 2 lamps? Well, what it does is, let's say the positive has a short to ground. So we have shorted to ground. So now ground is at the same potential as positive. Well, that means the voltage across this lamp now goes to 0 volts because it's the same point. Okay? But guess what? Look what happens across this lamp. Now the voltage has gone to the full system voltage, 135 volts. So what happens to that lamp? It turns on. And the lamp indicates that you have a positive ground fault. Very, very basic ground fault detection circuit. Okay. Obviously, the problem with having 2 lamps in series is eventually incandescent lamps burn out, and you can get false readings and can cause problems. So most charger manufacturers now use electronic comparator circuits inside their system. This still uses a resistance a potential divider resistance circuit that will cause the battery voltage to be half and half. So hopefully that explains why the ground fault is not always on the charger. So what you have to do is, if you do have a ground fault on the system, I know this is in an ideal world, but the first thing that you should do is this. Open each load circuit separately, and then watch the ground fault detection lamp on your charger. And whichever breaker you open that turns the ground fault light off, that tells you which branch circuit has the fault. Okay? If you really think that it's in the charger, the easiest way to confirm if the ground fault is in the charger is by opening this disconnect here. Okay? That takes away all of the load circuits from the charger. So if you open the output breaker on a charger and the light stays on, the ground fault light stays on, then yes, there is a problem in your charger and the ground fault is in there. But that is highly unlikely. It is much more likely that it's going to be a load circuit, and it could be in the battery if you have a really poorly maintained battery that has acid leaking all over the place. Then acid is conductive, and it can track down from a post down to the frame of the battery rack and cause a fault as well. So the easiest thing to do there is open the battery disconnect, and if the lamp goes off, then you know it's a problem with the battery. There is, obviously, to do this, especially open each load circuit, you have to take a load outage to do that. There are devices that you can use. Mega does one. It's called a ground fault detect circuit. And what you do is you connect a signal generator and send a signal between the pole of the battery or the charger that has the fault on it. You send a signal between there and ground, and then you put a transducer on each circuit, and basically you're hunting to see which circuit sees that signal that you're sending out along the ground path, and it can tell you without turning off the circuits which branch has the ground fault on it. They can be a little bit tricky to use, but I've used them quite a lot, and they're very good for finding ground faults without having to turn off the circuits. Okay, what's this next slide? Oh, my parallel chargers are not sharing the load. What's wrong? My pet peeve. Nothing. Well, probably. It is very, very difficult to create a circuit, especially when the load on your system is very low, that will make your chargers share the load perfectly. It's very, very difficult. Most charger manufacturers will say you have to have at least 5% load on your system before the parallel chargers will start sharing correctly. And that's if they have a load share circuit. But this phrase down here at the bottom is very important. The most important thing on any DC system is the float voltage of the battery. Okay, really the voltage of the system is designed to keep your batteries charged in at the best voltage, so losses and heat isn't caused. Okay, so and as electrical people, we should understand if this cable here is shorter than this cable here, then we're going to have a different volt drop on this top cable compared to this cable here. Okay, so let's say you set this voltage at 135 volts and this voltage at 135 volts, and let's say, just for ease, let's say the voltage drop of this cable is 0.5 volts, and we'll say the voltage of this cable is 1 volt. That means at the DC bus, this charger is putting out 134.5 and this charger is putting out 134. And whoever has the highest voltage is going to win. It's as simple as that. So rectifier 1 or charger 1 is probably going to supply all of the current to your load circuits. Okay? So many people will say, okay, well, what we'll do is we'll adjust the top charger down. Actually, we'll have to increase it to 135.5, and we will change this one to 136. And then we should have 135 volts there and 135 volts there. Yeah, in truth, you could do that, but there is always going to be some discrepancies in what's going on, how the load is shared, which battery here is taking the load, how hot this cable is compared to how hot this cable is. There are so many different factors that's going to make it that you can't absolutely make them share exactly. And in truth, it's not a point. What you should be doing is measuring with a fluke at the battery terminals. That's what matters. And let's say this battery here needs exactly 135 volts DC to be charged correctly. So what you would do is you would put your fluke on the battery terminals, not the charger output terminals. You wouldn't measure here. You would do it at the battery terminals. And then what I would do is I would open charger 1 and I would adjust charger 2 until the voltage at our battery terminals is 135 volts DC. Okay? So therefore, we know that rectifier 2, through all the cable drops and everything, is putting 135 volts out to battery. Then what I would do is I would close this breaker here, and then I would open this breaker here. And I would then set charger 1. So we have 135 volts at the battery terminals. So that means we know that with both of these chargers, they are putting out 135 volts to the battery terminals. And then what you can do is you can close both chargers there, and the batteries will be charged at the correct voltage. It doesn't matter if this charger here has 10 amps and this charger here has 2 amps. That's not what the concern is. The concern is the battery voltage. So a lot of people get sucked in, oh, I must have my chargers sharing the current. That is not correct. What you do want is the batteries to be charged correctly. Okay. So in this slide here, let's say this output here is 135 volts. This output here is 134 volts. Charger 2 will not supply current, but it is still online. Okay. And the battery is still being charged at 135 volts, which is good. So if you see 0 amps on this charger here and you're concerned that this charger here has failed, all you need to do is go, there's 2 things you can do. Either you can open the AC input breaker on the other charger, and this charger here will start, you should see this current go up. Once again, let's use 20 amps here. You should see, if you open the AC input breaker on charger A, you should see this go to 20 amps. Or another thing that you can do is near enough every charger system has an equalize button on it. So you would just press the equalize button on charger 2. That would increase the voltage to approximately 140 volts, which is more than 135 volts. So you should see the current increase on that charger there. And if that is the case, you know that that charger is good. It's a myth that chargers need to share a load. Forced load share circuitry is very poor at less than 10%, especially less than 5% rated load. Load shared circuitry does not work with temperature compensation. So if you have temperature compensation on your system, one battery could be at a different temperature than the other battery. And therefore, it's telling the other charger to increase or decrease its voltage accordingly, which messes with load share. Forced load share can cause issues with batteries being over or undercharged. And I've given you the best idea. Set both chargers at exactly the correct float voltage for the battery and leave them. Okay, that's the best thing to do. And the next thing that I hear a lot, my switchgear charger has low or no current. Okay. Remember, for a switchgear system, there is very little load in normal operation. Really, all that your charger is doing on a switchgear system is keeping the battery charged. Okay. There may be some lamps on the switchgear system that they need to power, and maybe some auxiliary circuits that may be powered off it. But usually there's about 2 to 5 amps maximum on a switchgear system in normal operation. So if you see low current on a switchgear system, it is not it is not a big issue. It's not saying something is wrong. Basically, as long as you have 135 volts and you see some current trickle charge to the battery, then you know everything's good. If you have 135 volts, then you have the potential to do work on the load circuits. So don't worry about that. Okay, it says any questions. One last thing I want to go through before I answer any more questions is the diode situation. Now, in most cases in a parallel system, they are going to have a blocking diode on the output, okay? The main reason for that, and we actually do this on our chargers as well, is we have to sense the voltage, and we have to sense especially if the voltage has failed. Now, let me just put this picture back up again. Let's say that this charger here, rectifier 1, has failed. Okay? Now remember, rectifier 2 is healthy, so we're going to get 135 volts at the DC bus from rectifier 2. And with that, all the way back to the charger terminals, we're going to get 135 volts DC. So even if rectifier 1 has failed, the sensing circuits inside rectifier 1 sees 135 volts. So it actually thinks it's okay in some circumstances. Okay, that's not good. And also, you know, the feedback circuit in our charger, it has to monitor the output from its charger to be able to change its voltage. So what we do is we put a blocking diode here. Okay, and therefore, if rectifier 1 fails, yes, we get 135 volts at this point here. It goes back to this diode here. We get 135 volts there, but on the anode of this diode, you'll get 0 volts if this has failed. So we can sense within the charger that the charger has failed. Also, what we do with the diode is we have a feedback circuit. So we have to monitor the output of this charger here at this point here. And let's say it goes up to 140 volts. We have to monitor that. And if we do it before the anode, we know, let's say this charger here went up to 140 volts. Well, with this blocking diode here, that wouldn't get back to the anode. If we see 140 volts on this side, we know it's our charger, this one here, that is putting out 140 volts. So our feedback circuit within the charger will say, okay, that's too much. Let's take it back down to 135. So it allows us to control each charger individually. So that's why we have blocking diodes in parallel systems. Some people call them, say that you should get auctioneering diodes. Once again, another pet peeve of mine, there is really no need. Like if you put it outside here, an auctioneering diode, and they say it's so the load circuits decide where to take its current from. That, to me, that's a load of nonsense. The reason why you should have a blocking diode is so you can separate the control signals from both chargers. Okay, let's go through the questions. Does a DC ground fault cause problems to the battery or charger? Very good question, actually. If you have a one single ground fault, that causes no issue whatsoever. Let me go back to our ground fault screen and I can explain it a bit better. Okay. So if you have a ground fault, all you're doing is tying, on this one here, you're tying the DC bus, the positive, to the ground. So because there is no current flow, it's not going to cause any problems. So now on this circuit here, the positive is connected to ground. What will happen now is if you have a negative ground, after you have a positive ground, then you will have a direct short circuit, which can cause fires or can cause breakers to trip. But a single fault on a DC system is not going to cause you problems. It's only when you get another ground fault on the other pole that you are going to have an issue with. And that goes back to, you know, this picture here where I said the man could actually touch one side. You know, you can, if you really wanted to buck trends and do weird things, you can connect the hot or the live of a secondary of a isolation transformer to ground if you wanted to. Okay, it's only when the other system, the other pole, then has a ground also, that you have a direct short circuit between the two, and it would cause things to trip. Hopefully that explains that question. How to find a ground which has a direction of 2 milliseconds and appears once per week or once every 2 weeks. Ooh, that is a tough one. Intermittent grounds are extremely difficult to find. If it's happening once per week, that tells me it's something on your load circuits. Something is happening on your load circuits once per week that is triggering a ground. If it's the first thing that I tell people, if it's an intermittent ground, the first question I ask is, has it been raining? Okay, because some DC systems get connected to analyzers out into the field. And what can happen is water can get into some of the terminations going to that analyzer, and when it rains, it can cause a ground fault. So I have seen that. I've also seen junction boxes, especially if they're explosion-proof junction boxes. There's a lot of thread, and when you thread the cap down on that box, it can trap a DC cable within that junction box and cause a ground fault. But if it's once per week and it's only for 2 milliseconds, oh boy, I don't know how you're going to find that, and I don't think it's on your charger. What you can do is if you can figure out roughly when it happens, you could turn your charger off and allow the batteries to supply the load. Open the output breaker from the charger, and then measure the polarity from voltage or from positive to ground and negative to ground with a fluke. And then when the fault happens, you can see it on your fluke. You can see that it's still, there is a ground. And if it still happens when you've isolated the charger, then you know it's something on your either your battery or your load circuits. But I don't envy anybody that has to find an intermittent fault like that. Could you please repeat, forced load sharing can cause issues? Okay, forced load sharing can't cause issues. I'm just saying forced load sharing is not, it doesn't work. Let's say, let me stop for a moment. Let's say you have a 100 amp charger, okay? Each charger is 100 amps and they're in parallel. What we're saying is that if it's lightly loaded, so usually that's 10% or less. So for a 100 amp charger, that's 10 amps. So you have two chargers in parallel. So your load would need to be taking at least 20 amps. So if you're not taking more than 10% on those charges, then the forced load sharing circuit just doesn't have the resolution to maintain a good balance between the charges at low current levels. It doesn't cause an issue. It just means that we cannot control the sharing between the two charges as well as when it goes above the 10% rating. Hopefully that answers that question. Another question is the DC panel with chargers and batteries connected covered under a certain article of the NEC? For example, you mentioned an oil pump application may have no circuit protection between the panel and the battery. Is that allowed by the NEC? That's a very good question, John, and I would have to get back to you on that. I'm not an expert on the National Electric Code, because unfortunately, in many of the situations that we work in the petrochemical industry, the NEC code doesn't quite apply to many of the industrial situations that we work in. Just local codes apply. So I can't answer that question, but I will ask engineering. I've taken a note of your name, and I will hopefully be able to get back to you on that. I don't know if you have a journeyman electrician, if he may be able to, because they should be up on the NEC codes. Maybe they'll be able to help you out with that. But I think the code definitely has something in there that says if the load circuit, if you can justify not having a disconnect in place, in other words, the load circuits are so critical that you don't want a break, then there are exceptions from the rules. Hopefully that answers that question. And the last question we have is, would this presentation be available to attendees? Unfortunately, our presentations have proprietary information in them. We do not hand out our slides to people, but you can rewatch this as many times as you want by visiting our YouTube channel, or you will be sent a link from Webinar Jam to watch it as well. So that is all the questions that we have. I hope that the presentation was of interest to you today, and I hope that you have ended the presentation knowing more than you did when you started. That is my aim whenever I do these webinars. We will send out a survey. Please do fill out the survey, and if you have any suggestions on what you would like us to present the next webinar on, then please do get in touch with us. We're always looking for some great ideas to present these webinars on. So if you can push us in the right direction, please do answer that question. So from everybody here at AMETEK Solidstate Controls, we thank you for your time as always. The next webinar will be in January, around about the second week of January. We will all send the invites out. We appreciate your time, and thanks again for taking the time out of your day to watch and listen. Take care, and bye.